Hello everyone and welcome to another video. Yes, I'm visible this time, so stop making fun of me on the internet that I don't know how to set up a camera. Alright, so welcome to this video where we are going to do some live coding and write a what we call as a data race detector. So we all know, because we are not filthy casuals, that a data race happens when two threads concurrently try to edit/read memory location, and then bad things happen if we are not synchronizing the access. And we do that by using mutex lock. Again, because we are not filthy casuals, we know that. Everybody knows that. If you don't, what are you doing here? Go read that. So if you already know that and we write thread safe code, how come there are so many problems on the internet? Well, the reason is that we all suck, and that's a consequence of being a human. I mean, for you guys, I'm not, I'm built different. So due to that, Google invested a lot of time to create this thing called ThreadSanitizer, which can detect data races. And I was on my way to home from office when I was thinking about this problem of detecting data races. You might be wondering why I was thinking. Well, because I used this at work to find a few interesting data races. So I was just thinking, how can we do that, right? Like, what goes within it? And so I came up with some solutions, and it happened to be pretty close to what Google does. So I was pretty excited, and I was pretty interested in writing my own. But why not write it live? Not exactly live, but on video, so that you guys can also learn. So that's what we're going to be doing. We're going to try to write a thread sanitizer, or rather data race detector. Data race detection is just a part of thread sanitizer as far as I know. I have taken inspiration from this. I have read a few pages about this, and this research paper, I mean, does this qualify as a research paper? I don't know. By Google, where they introduced the algorithm for their TSAN data race detector. So we're going to do that. And of course, it's not going to be production ready, but there's a lot to learn here. Also, we're going to be doing this in GoLang because it's an extremely simple language. And even if you have never used it, you will be able to catch on fairly quickly. Okay, so that's what we're going to be doing. With that said, I have a project open in GoLang, the superior GoLang editor. Don't argue about VS Code with me, or any AI code editor, for God's sake. So we have this, and what we're going to do is we're going to write it, and it's called T-SAN, but because I'm Asian, I'm going to call it T-SAN. But because it's going to be my creation, so I'm going to really like this, I'm going to call this T-CHAN. All right. With the cringeworthy name out of the way, let's begin. So we have a simple GoLang project, and I can run it like this. All right, so let's begin. So first of all, let's talk about what it's gonna look like. So let's take a step back. How do we even begin detecting data races, right? I mean, that's a pretty abstract, or not exactly abstract, but pretty hard to wrap around problem. So I'm gonna open this, whatever thing this thing is, and what, actually I don't even need that. So let me just zoom it a bit so that people don't complain. So here's what we're gonna do, right? So how does data race happen? Data race happen because of threads or go routines in GoLang, and then you prevent that using locks. Okay, let's keep it simple. We have threads or go routines, and we have locks. Go routines to add data races, and locks to prevent them. And if we use them correctly, we will not have a data race. If we use them incorrectly, we will have a data race. So that means we need to do something about these abstractions, or rather workflows, and hook some code into them so that we can detect data races. Maybe, I don't know. And also, one more critical thing. How does data race happen? Data race happen when we access memory. So we also need to hook into memory access. Okay. So let's say the goal for us is, if I write a thread is like, or go routines like, I'm not going to say thread, just assume it's a thread when I say go routine. Okay. So this is one go routine. Okay. And then I have another go routine. And now if I were to run this, wow, actually, let me just, I'm just doing something to make sure I'm actually able to print this. Okay, so we have this. It can print world hello, or it can print hello world any day, maybe, hopefully, whatever. It's not doing that, but we have two threads running in parallel here. Now let's say we had a, by the way, what a wait group is, it's like a semaphore. We have added two value to it. So now until this 2 becomes 0, we will wait here. And we subtract 1 every time we call done. And defer just calls it at the end of this function, this go routine. So only after these two go routines are finished, only then we exit it out of here and exit out of main. So that we are actually able to see the output of these functions. Now let's say I had a value. What I want to do is increment it twice. Okay, pretty simple. And then in the end, I'm just gonna print it. So what we'll see is this can either be 2 or, oh, wait, yeah, this can also be 1, right? But I don't think I'll be able to show that to you guys, no matter how many times I do this. Okay, whatever. But there is a data race. This is a variable that is not protected by any mutex. It's being incremented by 2 parallel go routines. It can happen that one increments it and the other increments it, but the result is just 1. So that's one thing. What we want to do is we want to run this program with our race detector and then have it tell us that there was a race. Okay, that's our goal. And then if we were to say, oh, okay, I'll forgive the AI this time. I mean, this is very trivial code. So obviously AI knows how to do this. And if we were to run like this, there should not be any data race. Now, right now we don't see anything, but there is, right? Now what I want to show you guys, first of all, if I were to not use this, right, this should show me an error. Okay, now if I were to run this using -race, it should fail. Yes, see. So this gave me a race that we read it at this line, but we are also writing it at this line. Okay, by the way, just so that you are able to follow, these are relative line numbers that I use because I use Vim. 15 means this is the line number 15, and this is like relatively how high it is. Function main is 10. Oops, right, 11, and then both. Okay, so just so that it's not confusing, it gets confusing for whoever is looking at my screen. Yeah, so as you can see at line 22 we are reading, but we had previously written at line 15. So this is the data race. However, if we were to do this, it wouldn't be a data race. And yeah, this works like a charm. So we know what we want to do, right? This is a very simple example of what we want to achieve. Now, how exactly are we gonna plug into something like this, right? So this is so there's two parts to this problem. This part one, that is the algorithm, actually figure out how and when a data race is happening, and then the second part to plug it into the runtime. Now, this is slightly non-trivial. Actually, both are slightly non-trivial, but nothing more than that. So we're going to do this in parts. We're going to first of all pick up the algorithm because that's the more interesting thing. For the runtime, if you want to add our own algorithm at the runtime, right, we'll have to either compile the source code or the other ways. So for now, what we're going to do is we're going to stay in the code itself and just add a few wrappers. So it would look like this. Wait. Okay, this should not be here. I'll just put it here. Okay, now I can go here quickly. Wait, this is my recording. Yeah, now I can navigate. So it would look like this. I have a function launch go routine. Okay, and it's gonna take in a function. What we're gonna do is, whenever we want to launch a go routine, instead of doing this, we're gonna say launch go routine. Okay, similarly, ouch, launch go routine. So why I'm going in this approach, right, is so that we understand what we are actually trying to do, and now the problem will start becoming clearer and clearer to you. Okay, we're also gonna have our custom lock. Okay, I'm gonna call it race detecting lock, RD lock. Okay, it's not read lock, don't confuse it. And I'm just gonna, yes, thank you very much. All right, so instead of creating a sync.mutex, we'll create a RD lock, and we're gonna do the same thing. Wait. Okay, we're gonna do lock and unlock. Okay, and then fine. So we have hooked into the runtime pretty much, right? Every time a go routine is being called, we can create a custom workflow routine. And similarly for locking, now we need for one more thing, and that is memory access. So every time we are accessing access memory, let's say this is the memory. Let's say we are doing it for integers to begin with. Okay, and how are we accessing? So we're taking that memory. We are doing some transformation on that, right? And we also say what's the type. So let's create a memory access type. So memory access read. So I'm just trying to create the API right now so that it is more understood what we are trying to do. So access type. So function, what is that? So every time we are trying to access memory, we are going to call this function. Now this way we have, what we have done is we have bypassed the need to do any editing in the GoLang source code. As long as the target source code is using these wrappers, right? These are essentially wrappers. As long as that is happening, our data race detector should work. Okay. And yeah, this becomes something like this. Let's see. Access memory, right? We are trying to access X. We are trying to increment it, and it is a write. That makes sense? I think I have to write it like this. That makes sense. What's the warning? Always check your warnings. Unwrap. Okay. So this is what it becomes. And now that we are using only our constructs, this should not detect a data race. We're not gonna try to wrap weight group for now. We're just gonna assume weight group works properly. So the reason is we're trying to narrow the scope down so that we can actually approach the problem. Once we approach the problem and we solve it, then we expand the scope. Speaking of narrowing the scope, there are many things in GoLang that helps with synchronization. By the way, this is gonna be a very important thing to read if you're interested. So whenever you're trying to create something like data race detector, you have to know what is the memory model. And memory model formally just means what is the behavior of concurrent threads or go routines in this case when they are accessing memory. Okay, how it is observed by one routine, go routine and another. Okay, that's what it is. And there's a lot of nuance to it. So whichever language you are trying to target, you want to understand its memory model. I've already read this, so I'm fine. Don't know about you. But basically, there's a lot of things. For example, there's a channel in Go. There's signal, weight conditions. There's a lot of things. And again, we have to narrow the scope to solve the problem first, and then we can expand it. Okay. So what we're going to do is we're going to say what the primitives are, right? So concurrency primitives. These are first Go routine. So we know how to launch a Go routine. Second, mutex lock. That's it. We are not going to have condition variable. We're not going to have semaphore. We're not going to have anything. Okay. I think, can we? Okay, maybe I think we might need condition variable. I'm not sure. But initially we won't even think about it. Let's say P1. I am so corporate build that I marked it P1. These are P0 obviously. Right? So these are the primitives. There's no such thing as a semaphore in our world. There's no such thing as a channel. There's no such thing as a sync.once. There's no, those things don't exist. We are implementing our data race detector for these things, and you will understand how it can be extended to other things. Okay. So I think we have finally addressed the problem of explaining the problem. Cool. So let's try to do something very quick and hacky. So let's actually look at this problem, and this is not the way I approach problem solving, but I call this overfitting on sample. What that means is I have a sample test case. Can I figure out an algorithm that works for this? Let's see. So when I used to do competitive programming, this was like a big problem. Many times people would look at sample test cases for a particular problem, and they will overfit their solution to that. And so that is why, like, after a point I stopped reading samples all, like, at all. I stopped reading samples. I would just look at the samples when I have to submit or test my code. So I don't really approach problem solving like that, but whatever. It's a decent way. So if you look at this, right, we are accessing some address X, and we are accessing some address X. If you're accessing it in parallel, that means multiple Go routines are accessing it. And really, if they are using a lock to access it, it is fine, right? Right, it's fine. So what do we do? So what if, actually, I want to stay here. So what if, I think I can do some drawing like this. So I know that I'm trying to access some memory X here. Bro, I just want to draw. Let me draw. Okay. So I want to access. Yeah, so I want to access this memory. And I know, like, just to clarify one, right? We are creating a data race detector at runtime, not at compile time or post runtime. There are three ways to create a data race detector. We are doing it at runtime, just like Go-race does. Okay. So at runtime, we know we are trying to access X, and we also can probably know which Go routine is accessing this, right? And we can also probably know which logs this Go routine has already acquired. I mean, this is something we definitely need to know. So if that is the case, what if we check that, okay, if Go routine 1 is accessing X, just a second. Okay. If Go routine 1 is accessing X with lock A, and go routine 2 is accessing X with lock B, then we would know that there can be a race, right? I mean, it's not completely correct, but we are making some progress. And really what we need is we need an intersection of lock. Like it could have acquired B, C, D, and we would still have a race. But if it also acquires A at some point, then we won't have a race. So let's try to do that, okay? Let's go ahead and so first of all, we need to know this information, right? What's the go routine and what's all that crap. So we're gonna have to do some bookkeeping and a bunch of bookkeeping actually. So how to get go routine ID? Do we have this? I want to know. I am a human. I mean, I'm built different, but I am a human. Okay, we have a runtime.go ID. Okay, so that means we have this identifier that we wanted to know which go routine is working. Now we also need an identifier for this lock. Well, that's very easy. We can just have an ID, right? So let me just create. So I'm not going to organize the code or anything like that because I don't have time, but get an ID factory. Sorry for the naming, but function get ID. What? Okay, I had caps lock on. Where ID factory mutex. So basically, because everything can be happening in parallel, we want to generate this ID uniquely. We don't want race, so I'm gonna use actual mutexes to make sure I'm doing things correctly. So get ID is just gonna be where current ID, current ID. Yeah, let's just call that. I'm gonna acquire this and I'm gonna say current ID plus plus. I'm gonna return this ID. So now, whenever I'm gonna have a new actually I don't like this name RD lock. I'm gonna call this T-Chan lock. The name of our project is T-Chan. We're gonna embrace this cringe, okay? So new T-Chan new T-Chan lock. We're gonna get an ID. Oh my god, I don't know how to code. Oh wait, I named it int. Okay, I know how to code. All right, I'm already returning it. So now we have an ID for this as well, and we have an ID for go routine as well. So actually, let's create some state. This is gonna be our global state. That our race detector will have. I'm just gonna create a global variable because I don't care. I'm a thug like that. So whenever we are gonna need to do a lot of bookkeeping, right? So this global state is gonna help us do that. Okay, so let's see what can we do. So when we lock, right, let's get the go routine ID. What was that? Go ID. Wait, there's no such thing. Yeah, there's no such thing. Oh, that was a question. They deliberately chose not to provide it. Okay, that's fine. What we can do is whenever we launch a go routine, we can assign it an ID, and actually that go routine will get the ID like this. Okay, so I'm gonna get an ID, get ID, and then I'm gonna call that as a go routine. So this function will have its ID. So call it GID. Okay, actually I'm just gonna call it go ID. Okay. So now whenever we are locking and unlocking and all that crap, we can pass this around. Okay. Actually, some work has come up, so I'm gonna have to do a cut. All right, I'm back. So where were we, right? We had figured out how to get the runtime ID. We had figured out how to get an ID for a Go routine and for our teach and lock. Now we need to use these IDs to run our algorithm. And it just came to me that I don't have the image. So I'm just gonna go over here and yeah. So thread 1 was accessing X with lock A. Thread 2 was accessing X with lock B. We need the intersection of A and B to not be empty, right? This is our algorithm. It's not correct, but let's get started and then we'll improve. So, so when we launch a Go routine, we get an ID and we assign it. We give it to the function that is running in the Go routine so that it can use it. So when we lock, let's also take the Go ID. Wait 1 second. I am curious. What is the okay? We are implementing the locker interface. Who implements so many people? Okay. So we take Go routine ID and then we will do the bookkeeping. And similarly, we can unlock can also take Go routine ID. Now you might think, okay, this is very fragile, and it is fragile. Like anybody can pass anything wrong, but that's all the language support we have. We will fix it. We will improve upon it. We won't have to do all this wrapping, but to begin with the algorithm, we have to do this. Okay. All right. So lock and unlock has this, and now lock can take this Go ID. This can also take the Go ID. Bro, I don't know how to use Vim. So now we have Go ID, and now we can actually do our algorithm. So for every access, we want to figure out what are the already acquired locks. So memory access is happening by a Go routine. Again, that needs a Go routine ID, right? So let's go over here and take a Go ID. We just assign it here and here. And now, so whenever we are accessing Go ID, what we want to do is we want to get A, that is again set of locks acquired by X T1, and then we want to get set of locks acquired by that. Okay, but this access memory is happening across time, right? So that means let's have a simple global state. First of all, what is the lock set for our Go routine? So it's gonna be a map of ID. So this is Go ID. Okay, I'll just have a whatever. I want to do this. And this has a set of lock IDs, right? So do we have a set? We don't have a set, so let's just have an array of lock ID. So we're gonna keep this. Let's have a global init function. So init tchan. All right, I'm gonna say global state is equals to make, come on, AI, do your thing. What a clown. What a clown. Okay. What's the problem? Do I have to do this? I don't think I have to do this. Okay, it's not. State is equals to global state. No, poorly written code. So So this way, whenever we try to acquire any lock, what we want to do is we want to push this lock to the array. So what we're going to say is so something like this: global state go id dot lock set go id equals to this, right? That makes sense. This is pretty much what we wanted to do, and this is wrong. Okay, now this is correct. So, and whenever we want to remove it, actually let's just lock id set, or let's just say lock set. It's a map of lock id to bool, or we can just have a struct. So I'm just trying to create a set, which is because we don't have a map set type. I'm just using a map. I'm gonna say lock set. So lock set, I'm gonna make a lock set and this will, honestly, I wish there was a set type. We don't have a set type, unfortunately. It's gonna be a bit bad. So if okay, let's just say ls is global state dot lock set. Now if current lock set, if we don't have a lock set, what we want to do is ls go id. I'm just making sure ls go id dot okay, print set. Now print set dot add. I mean, sorry, I'm pretty bad at Go. So what we're doing is, for whenever we try to acquire a lock, we just say that for the lock set, we are going to add this lock into the lock set of this Go routine. Okay, pretty simple. Here I'm just making sure that lock set exists for that Go routine. So I'm just going to say this is my bookkeeping. What book okay. I got completely out of the flow. Then what we just want to do, we're gonna have a actual lock. So think dot mutex, and then we're just gonna say r dot lock. I cannot type. Oh, I am. Let's just say, nah, I don't care. Let's just say inner lock. So I'm wrapping over an actual lock. So let's do the same bookkeeping now. Now here, this must always be true. Let me just make a quick function, a third condition. Let us do this. If not condition, panic, assertion failed. And I just want to have a message template and args. All right, this looks good. So what we can do is basically every time we are unlocking, we know that this lock set should exist, right? So I'm just going to assert okay, lock set can't be empty, bro. Okay, and we are just gonna delete this. So to remove an entry, we just do delete. I hope you guys are able to follow GoLang, even if I'm not. Wait, logset for, or rather, logset for. Even though I'm using GoLang, and if you don't know GoLang, you should still be able to follow. I mean, it's pretty simple. It has very few things. We are deleting an entry. So now we are keeping a track of what are the logs. Okay, so just for the sake of it, let's try to print what logs we have. Okay, so before we do this, all logs for go routine, and then I'm gonna say go routine this is what are the logs, current set, right? Have I done anything wrong? Bro, I'm just gonna use the print f all logs for go routine are so every time we acquire anything and unacquire anything or unlock anything, we're gonna just print the logs we have. Or actually, let's print the entire log state. Okay, so that we know what are the logs each go routine has. Now let's run this. Oh, it's gonna fail because I'm not. Let's just perform. Let's just do this. This should fix it. Wow, what's the segment fault? Global state. Okay, I need to call init for our tchan. Uh, okay, if not, okay. Ow. Okay, third, okay. Bro, how have I not been able to code something so simple? I'm not this bad usually, I'm worse than this. Oh, am I running this with GoRace? I was running this with GoRace. I'm stupid. We are making our own race detector. We don't need this crap that Google has churned out to the world. Yeah, so actually let's also print a new line. Print a new line. So first of all, go routine 2 acquired it. And as you can see, what? So ID factory never gives 0, right? It always starts with 1. Okay. Why do they have 0? Bro. Am I doing something stupid? The log set is map of log. Let's make it a bool. I don't care about the 1 byte I'm saving. So initially, go routine 2 tried to acquire. Why do we have? So why is 0 there? Every time we launch a go routine, we are launching with bro, no. launching with ID1, launching with ID2. Why is this showing 0? If the RID I'm getting wrong, am I sending wrong RID? Sending go ID, go ID, go ID, go ID, go ID. The go ID I'm getting. Interesting. Let's actually print it here. Launching. This should be go ID. I don't know. I'm doing something stupid. I know that for sure. Launching with 2, launching with 1. Then we'll try to acquire the lock. As we acquire the lock, we get the lock set, which is an empty map. And then we try to get it for the go ID. If it is not there, we create it. This can be the problem. Oh. Okay. I'm not using new teach and lock anywhere. I knew I'm doing something stupid. Because that's otherwise it was 0. Okay, so the lock ID is 3. And wait, what? No, lock ID is 1. As go routine 3 acquires it. And go routine 3 acquires it. All logs for go routine, go ID. Okay, actually, so one thing, I'm pretty stupid. What we are doing here is we need to handle concurrency. So let's have a global state lock, where global lock, I'm gonna have call this mutex. So every time I wanna work with this, what I wanna do is glock.lock and unlock. Similarly, glock.lock unlock. Notice that as we assert, we might exit without unlocking, but that's fine because we are panicking. So notice I actually want to do this printing right here. This will help us get the correct picture of what we wanted to see. So we launch go routine with 3 and 2. First of all, 3 starts. It says, okay, 3 has acquired this, then 3 exits and it removes it. 2 starts, 2 acquires this, 2 starts, 2 exits, 2 removes this. If we run this again and again, okay, we are not seeing any variability. So to add some variability, what I'm going to do is time.sleep, we're going to add a sleep for a millisecond so that we actually see some difference in execution every time we run. Okay, not here actually, where we should do this after accessing the memory. So notice, first of all, 3 acquired it, then 2 acquired it. So now both of them have that, and then 3 removes it, and then 2 removes it. So now we are tracking which thread or which Go routine has currently acquired which locks. Now, oh, not postman. No, please don't reveal anything secret. No, get out. Get out. No. The APIs I used to hack NASA. No, please don't show yourself. So, but here, this is more of a cross time property that anytime X was accessed using lock A, we want to make sure that any other time X is accessed, it must be using B. So how we can do that is the first time, let's say X is accessed. Wait a minute, can I clear this? How do I clear this? Wait, why is this eraser so bad? Oh, I have this. So anytime X is accessed, let's say using L1, L2, L3, we know that, okay, X needs these for protection. Now, let's say X was accessed using L3 and L5 and L2. Now we see, okay, X was accessed using this. Now, really, L1 doesn't matter. L1 is not helping with mutual exclusion. L5 is also not. L2 and L3 are only helping. Now, let's say X is accessed using L3. Only L3 was the one that helped with the concurrency lock. And if at any point of time, X is now accessed with L7, that's not gonna be safe. Now we are assuming that all these Go routines can be running at any time, any point in time, which is of course the problem we mentioned we would have, but let's get something working, right? So for X, now how do I track that? What does the variable X mean? Well, we need something like a unique property about X. What is a unique property about X? It's memory address. Actually, there's still a caveat with this. When you get a memory access using malloc or new or however way you get it in GoLang, when you free it, that memory becomes free for use and it can be reallocated when you do another malloc or new or whatever method you use to get memory. That means we also have to distinguish between incarnations of that memory, but we're not going to get into that. So for a variable, what we want to store is the set of locks that were used to acquire it. So let's see. We're just going to call that variable lock set, which is a map from any address to it's a set of locks. Okay. So as we access a memory, right? Let's see. We want to perform fx. That's fine. Now what we want to do is we want to do something similar to this. We acquire the lock. We get the lock set to be variable lock set. Current set would be whatever the value of X is, right? So get int address of variable info. How to get that? Okay, we can just do that. So no, it won't work like that. I need to do something else. I think I need to use reflect. This won't work. I want to get that in variable. Does this actually work? I don't think so. Let's just quickly check. I am a Go expert. Don't you guys know? That does print it. And now if I were to create a map of integer 64 to, let's say, Boolean, and then I say this does not work. Is it U in 64? Yeah, this is not working. How to get address of variable to integer? Yeah, it doesn't give you the address, it gives you a reference. I think reflect can give that value of dot address. What does this give you? So value of gives you that, and then the unsafe address. It's the uint pointer. Yeah, that looks like correct thing. So sorry for that. I just forgot to commentate. So this is the type. I think it's just it's 64-bit probably. So we were here, right? So let's just say address is reflect dot value of x dot address, sorry, unsafe address so we get that. So if we have not created one, then we're going to create it, and then what we're going to say is current set is equals to ls address, and then current set not go id. What we want to see is what are the locks that are currently acquired by this. So see, when we were accessing X, we looked at what are the locks acquired by this, and we keep a track of that. So current set for this address, not this address, but wait, yeah. So we want to add all the locks. So for lock ID range, global state go dot lock set go ID. Bro, I cannot type. So whatever locks this go routine has currently accessed, we are gonna say what is that is the current locks is this is just this. So this is the current lock, and this is the previous lock, right? Now we want to take an intersection of this unless previous lock was nothing. So if this was the case, then I'm just gonna make a quick copy set rather. I'm gonna take a set, copy lock set. I'm gonna return a lock set. I'm gonna make a result. Then this should do it for me. Thank you very much. This works, right? Yeah. So if it was nothing, then ls address go id, no, not go id, what the heck, is equals to copy lock set global state dot lock set for the current go routine. So I'm just saying these are the current locks. These are the current, or rather current go routine locks. These are the current go routine locks. We check the lock set. ls is just not a good name, but okay. So we check what are the previous locks. If there were none, we just assign it to the current one. Or actually, let's just say, let's just copy here. And then we just can say current go routine locks. And we wanna glog.unlock. What we wanna do is return here. Otherwise, we wanna take a intersection of these two sets and set that, right? So what we wanna say is set intersection of previous locks, that is this, and the current go routine locks. And then what we will check is if length of previous locks is 0. If this happened, then we have a, we can just say data race, right? Data race for variable with address. We can say that I will, okay. Yeah, GoLang is not the most ergonomic language for sure. That would be like this. So this will always panic. This will always exit. So unreachable. I'll just do that. So this looks good, right? So whenever we access, we check what were the previous locks that were used to read this. If there were none, we assign them to whatever is the current one. Otherwise, we take the intersection of them. And if it is nothing, then we say there was a data race. Now, this means that let's quickly implement set intersection x y. Okay, now for kv, if this has it, right? So if y has k, then I'm gonna say result. So this way, we can get an intersection between sets, and this should work. Now there's a lot of gaps right now, but let's just try to run this and see what happens. Unaddressable value. Let's try that. Yeah, getting to the address is so difficult. Let's try that. Ah, not this. Okay, let's just ask Chat GPT. How to get uint pointer address of a integer pointer in GoLang. I'm sure it knows that much. Oh, unsaved dot pointer. I see. That's what we wanted to do. Hmm. I thought we would remove it. What happened, GoLang? I thought you were good. So, where are we assigning? We don't want to assign. Wait, what do you mean assignment to nil entry? Okay. Yeah, we never created where lock set. Let's just get rid of anything. Wait, it didn't get rid of it? It did. Unlock of unlocked mutex. That is probably because I forgot to remove this. Thank you. Let's run again. And we did not see a data race. Although I think we should have, right? No, we shouldn't have. Now, if we were to not do this lock in one of the threads, we should see a data race. And we did see a data race. Failed data race for variable. We have correctly found a data race. So what's happening, right? Let's go over it once again. We launch a go routine using our wrapper. We get the ID, we have the ID for that. We send that, and whenever we are trying to access the memory, we send that. So we check what were the accesses for this way. What's first of all the current go routine locks, and we check what locks have been used to access this go routine, and then if this go routine, if this variable is being accessed with some completely different locks, then or basically no locks, then it is essentially not a problem, right? Wait a minute, my OBS, is it crashing? No, okay, it's not. So essentially then it's not a problem, and so that's how we figure out if there was a data race or not. For example, to demonstrate that, let's create lock 2 and use lock 2 for locking. So we are using lock for both of the memory accesses, but we are not exactly unlocking. I mean, we're not exactly using the same lock, so it should still give us a data race. And as you can see, it still gave us a data race. And we can even print some things like this. So, or rather, actually, we still need to do something. So, new locks, lock intersection. Let's also previous locks used and current go routine locks. Previous locks used is ls address, and current go routine locks is this. And if this does not happen though, then ls of address is lock intersection. As you can see, previously the locks used were 2 and current go routine has lock 1. So okay, so we are doing that. This much is working, but this is not even close, right? There are a lot of problems. For example, what we have assumed right now is that anytime a variable, like when a variable is being accessed across these Go routines, we are assuming that these accesses can happen at any time. These accesses can happen at any time. Oh, what? Bro, where is this? Okay. This is all right here. So here's the problem. Let's say in Go routine, so Go routine 1, Go routine 2, Go routine 3, and Go routine 4. We are only going to talk about X. Let's say X was accessed here, and then it was, and let's say it was accessed using a mutex lock or without a mutex lock. Then it was accessed using mutex lock M1. In Go routine 2 as well, X was accessed using M1. In Go routine 3, M1. Go routine 4, M1. As per our algorithm, it will fail. Why? The reason is that it will see that, okay, here we are acquiring a lock, here we are not acquiring a lock, so this is a data race. And this is true if these two can actually happen concurrently. But what if this is, let's say, some setup stage where we are accessing X, then after the setup stage only, all these other Go routines actually start, or rather, like, these Go routines actually start. This Go routine was anyways working, so we know that this x-axis always happens before this, and only this x-axis happens concurrently with these. So in that case, this is not a data race. So these relationships we are not considering yet. We were considering that any access across Go routines is concurrent, and that is a flawed assumption. So what relationship are we actually targeting? And the answer to that is happens before. That is, so it's a relationship that we can tell between memory accesses, that a memory access happens before another memory access. And if we were to use that, we can figure out the solution to this problem, and then we can extrapolate that, think about more cases, and figure out this problem. But for today, I think we have made a small dent in the problem. We will continue later. With that said, see you. Have a nice day.